So good afternoon, and we'll start today's FM lab class for a bit batch. Okay. Uh, Nihal, can you ask the others to join fast, please?
Yes, sir.
Okay, fine. So we'll start today's class. I hope you remember that last class we started the turbines. So we have done the Pelton turbine. So I told you that Pelton turbine is an impulse turbine and it has hemispherical buckets on its circumference, and it has a nozzle through which high velocity water enters and hits the buckets. Thereby, this high velocity water will make the buckets to start rotating, to rotate. From there, the RPM is developed, which is nothing but mechanical energy. And to the shaft of this turbine, you will attach a generator. So both the turbine and generator will be on the same shaft. So when that happens, all the energy, mechanical energy developed in the turbine will be sent to the shaft. So through the shaft, the generator generates the electrical energy. This is the procedure for any hydroelectric power station. And if you go to some interview for some power station as a assistant executive engineer or something, they will ask you this question: how is power generated? You will have to explain it this way. Yeah. Then that is about the impulse turbine. It is called impulse due to the impact, and there is a nozzle. Kinetic energy is there. High velocity water jet is going to hit the buckets. Fine. Whereas in the case of a reaction turbine, there is no nozzle, there is no kinetic energy. Instead, we utilize the pressure energy created inside the Francis turbine. So I will just show you the diagram of the Francis turbine. Are you able to see?
Yes, sir.
Are you able to see the turbine?
No, sir, we can see G.
Wait 1 second. So same thing is happening. You are not able to see a turbine? 1 second. So something around here. What happened to this? There's some problem. Not. Yeah. You able to see now?
Yes, sir.
Yeah, fine. Now look at this. See, this is the Francis turbine, and it is similar to the centrifugal pump. See the look at the shape. See the Francis turbine. This shape, this particular shape, this shape, this curve like this is called a involute shape. That geometry is called involute. Okay, so it has an involute shape like this, and in the center you have the wheel or the impeller. Now, after this impeller, here you have got certain blades here. These are called as guide vanes or guide blades. Okay, here. Now this starts rotating and this is inside a casing. So water will enter from inside and it fills up half to three-fourths of the level with water. Once that happens, this starts rotating. This wheel starts rotating due to the pressure energy, gains momentum, and starts rotating at high speed of 30 to 40,000 RPM. When that happens, these guide vanes, what they do, the function of guide vane is to direct the water onto the runner. This is called the runner or wheel. It directs the water onto the runner so that the water does not get wasted by going in hitting somewhere to the casing. Instead, it makes the water to fall onto the runner. Okay, onto the runner. Thereby, the water is not wasted. You can generate the power or the mechanical energy you can generate. So that is the function of guide vane, or it is called guide vane or guide blade. Okay, this is called a volute casing, and this geometry is called an involute. Okay, now just as you have in the case of Pelton turbine, the water is going to enter here, but there is no nozzle. Observe, there is absolutely no nozzle, no kinetic energy. But the pressure energy is utilized to run the turbine. So the wheel starts rotating and generates RPM. Then here you have got the shaft. This shaft is connected to the generator. And whatever power is generated in the turbine is sent to the generator, and from there electrical energy is generated. So what is the difference between Pelton turbine and Francis turbine? Pelton turbine has a nozzle, Francis turbine does not have a nozzle. Pelton turbine is impulse turbine due to the impact or kinetic energy of the water, whereas Francis turbine is a reaction turbine and depends on pressure energy of water. These two are very important things. Second one, third one, sorry, Pelton turbine, you have tangential flow of water. Whereas in Francis turbine, it is radial flow of water. You can observe here, isn't it? The water is flowing radially outwards from the center of the shaft. So these are the basic differences between a Pelton turbine and a Francis turbine. Okay. So, but both are horizontal turbines. You can observe shaft is horizontal. Okay. So with this in mind, let us go to the experiment. Are you able to see the manual? Yeah.
Yes, sir.
So let us go to the Francis turbine experiment. Okay. Why I showed you the geometry of Pelton turbine and Francis turbine is because they're going to ask you the differences between these two turbines in the viva of your practical exam. That's why. Okay, you have to be prepared for that. Okay. So now let us come to the experimental setup. Now, what is our aim? To find efficiency of the Francis turbine and to draw the operating curves for different load and different speed. So we told you, for different load and speed. Last time we did constant head and constant speed. No, similarly we have to do for Francis turbine also. So this is the setup. Okay, this is look at this. Here there is a sump. Sump is underground water. Okay, then here you have got the motor, the pump, which is going to pump the water. Here you can observe there is a venturi meter. Can you see this shape? Convergent divergent nozzle, throat, convergent divergent nozzle. Okay, this is a venturi meter to measure the flow. Then you have the control panel, and from here the water will come. Then here you have got the Francis turbine, and here you have got the draft tube. Now, draft tube is very important. You don't have draft tube in Pelton turbine, but in Francis turbine you have draft tube. Why? What is a draft tube? A draft tube is what you call is instrumental in helping the downflow of water to the tail race. Now, as you know, after work is done in the turbine, the water flows and comes out through the drain. There is negative suction pressure below. To avoid that, they will keep a draft tube which is conical in shape, that is enlarging diameter. When that happens, the water flows out through the draft tube with a velocity and does not create any pressure difference. Okay, there is no low pressure created here. Now, why low pressure is created? When there is air block or vacuum, what happens? The water does not move because due to the air block. Because of that, hammering takes place it's called water hammer. The water is going to hit the pipe and make a sound, which is not desirable. We don't want that one. Okay. So to avoid that, they will make the draft tube in a conical portion like this, so that once the water comes out, it will enlarge and there is increase in pressure. And there should be no vacuum, and water hammer should not occur. And cavitation also should not occur. What is cavitation? Formation of bubbles. We don't want that one also. Okay. So this is the setup of the Francis turbine. Then observe here, you have got the electrical switch here. You have a series of bulbs placed here. Now, can you tell me one difference between Pelton turbine and Francis turbine in the method of loading, electrical loading you have here? See, here you have electrical loading. In the Pelton turbine, you have dynamometer loading. You remember Robrek dynamometer. But here you have electrical loading. What do you mean by electrical load? If you switch on one bulb, it will consume some 10 watts, 20 watts like that. That is called load. That is the electrical load. Then you have here energy meter reading, a starter, voltmeter, vacuum gauge, pressure gauge reading. All those things you have parameters here. Remember, this is a group experiment. 3 to 4 people will be there for this experiment. One fellow will be taking one reading from the control panel, another fellow will be taking the suction pressure, delivery pressure reading, etc. Okay. So all of you should know how to take all the readings. Okay. Yeah. So let us come to the experiment. So switch on the turbine. Water will start flowing, and we'll make the table of observed readings. Now you already know there is one constant head and there is one constant speed. So we will do the experiment in a similar way to Pelton turbine. Only difference is in Francis you have electrical loading. In Pelton you have mechanical loading using dynamometer. Okay, that is the major difference between this and that. Okay, now let us come to the Francis turbine. Now in the Francis turbine, you have got constant head and constant speed, and for vane opening and valve opening, both are same. So for each valve opening, we will be doing what we call taking the readings. Okay. So trial number 1, 2, 3 for different valve openings. That is same thing. Quarter, half, 3/4 full, like that. Okay. So we will do the readings for quarter and half. Okay. At constant speed, and note down the pressure gauge reading and vacuum pressure, H1 and H2 difference. Now there we had F1 and F2. Dynamometer loading was there, force. But here, load and generator is voltage and current. Note down voltage and current. There only in the control panel you can note it down. Then wattage. What is wattage? Power. Power is equal to voltage into current, V into I. Then time taken for 5 revolution of energy meter, capital T, so many seconds. Okay. So make the valve opening quarter, write down all the values. Make the opening quarter half, note down all the values. We'll do for 2 sets of readings. Similarly, constant speed. Same, repeat, same tabular column. Keep the speed constant. And for 2 different openings, quarter, half. Take all the readings, do the calculation. Now, coming to the calculation, then put everything in the calculated tabular column. Now, loss of head H is equal to, formula is same. H into SG minus SW. You are familiar with this. Then Q. See, we have venturi meter, so with the discharge of water is flowing. Yeah, you have the discharge. So the same formula, A1, A2 root 2 GH. Now, A1 cross section at inlet, A2 cross section at throat. A1 is with respect to the venturi meter inlet, diameter D1 is equal to 25 mm. Note down, diameter D1 is equal to 25 mm. Similarly, A2, cross section at the throat of the venturi meter. So D2, diameter 2 is 12.5 mm. Note down, D1, 25 mm, D2, 12.5 mm. Then, input head HM is equal to 10 into P. P is the pressure gauge reading in kg per centimeter square. If you multiply by H, I will get the water column H in meters. Then input power P, PI, WQ HM by 1000. W is rho into G. Q is the discharge. So you found out Q here using the venturimeter formula. Then HM is the head on the turbine. How much is that? How did you get HM? 10 into P, that is HM. So input power is got, then brake power. Observing the brake power formula, everything is what? Constant. Only this capital T is changing. Okay? So note down that one. Okay? And you can write down input power and brake power and calculate. See, brake power you can calculate. Output power or brake power, you can get this value. Input power, you can get this value. Output by input is efficiency. Now, don't see this one. What is that? Torque and this is a mechanical loading. This is not required. Not required for you people. After calculating output input power, calculate efficiency. That's all. Then unit quantities are there, which are a unit speed, unit power, unit discharge, specific speed. You can keep it and draw the graphs, whatever they are given. That is Q versus BP and Q versus overall efficiency, etc. So it's very simple, and you can do the calculation now. Now, is there any doubt in what I have explained? Hello? Is there any doubt? Okay. So then you note down the tabular column. Constant head, constant speed for Francis turbine. Note down the tabular column. I will give the readings. Okay? Yeah. Meanwhile, answer your attendance. Chaitanya Vamshi,
Present, sir.
Karamjit,
Present, sir.
Kartikeya Avasti,
Sir, his mic is not working. He put chat.
okay. Kiran V, Mastanullah, Mazin Umar, Yan Sharan, Narendra Sadanand,
Present, sir.
Nihal Shetty,
Yes, sir.
Nikhil, Himala Vagesh, Nitin, yes. Prajwal, Prayag,
Yes, sir.
Prince Prabhakar, Prince Aloy,
Yes, sir.
Rakshit, Rishi Dineshwar,
Present, sir.
Sandeep, Sanjay Gowda, Sanjay Yan,
Yes, sir.
Satish Shankar, Sadaf Khan, Suman Xavier, Vijay Kumar,
Yes, sir.
Zahir Hussain, okay. Please copy down the tabular column. Make two columns, one for constant and one, two similar tabular columns, one for constant height, one for constant speed. Right. So we completed tabular column. Hello. Hello.
Yes, sir.
Completed.
Yes, sir.
Okay, fine. So I'll give you the ratings now. Okay. So let us start with constant head. Right. So Francis turbine, take down the readings. Okay. Vane opening, make it quarter. Vane opening quarter, constant head. Constant head, vane opening quarter. Note down the speed. So 3 trials are there. So for quarter opening, note down the speed. First reading of speed 1160, 1160 RPM. Second 1059, 1059. Third reading 972, 972. Next pressure gauge reading 0.2. Second reading 0.2. Third reading 0.2. Pressure gauge reading 0.2 for all the 3 sets. Next, vacuum pressure 40, 40. Second one 40, third one 50. Then head over V notch H 0.25. H1, I'm talking about H1. First reading 0.25, second reading 0.2, third reading 0.2. H2, first reading 0.75, second one 0.55, third reading 0.5. Then voltage, first reading 150, 150. Second 130, 130. Third one 120. Then current, first one is 2, second one 2.5, third one 3. Okay, now here they are not multiplying the voltage into current to get the power. They are taking the wattage of the bulb. Okay, okay. The next section. Okay, so first one 200, second 400, third one 600. Wattage of the bulb 200, 400, 600. Next, time taken by energy meter for fire revolution. First reading 130, 130. Second 75, third 55. All of you noted down the readings? Any doubt?
Sir, can you repeat it?
Repeat which one?
H1, H2.
H1 0.25 first reading, 0.2 second reading, 0.2 third reading. H2 0.75, 0.55, 0.5. Shall we go to the next set of readings? Okay. Next one is vein opening. You can call it a vein opening or valve opening, whatever. So second one is half kick, half vein opening. So again, 3 trials here again. Right. First one, speed 1167, 1167. Second one, 1062. Third one, 973. 973. Okay. Next, pressure gauge reading 0.2. 0.2, 0.2, 0.2 for all the 3 readings. Now vacuum pressure 40, 40, 40. Then H1 0.25, 0.25, 0.2. H2 0.6, 0.55, 0.5. Then voltage 150, 150, 130, 130, 120. 120. Current 2.5, 2.5, 3. Bulb wattage 200, 400, 600. 200, 400, 600. Time taken for 5 revolution of energy meter 140, 140, 75, 55. Yeah, all of you got the readings? Any doubt? Shall we continue? Hello? Shall we continue? Okay. Let us go to the constant speed now. This was constant head. Let us go to constant speed. Now constant speed will take the reading for 3/4 and half. Okay. Vein opening 3/4. Speed 1000 RPM. Pressure gauge 0.1, 0.2, 0.3. 0.1, 0.2, 0.3. Then vacuum pressure 40, 40, 40. Okay. Next, H1 0.1, 0.1, 0.2. H2 0.4, 0.45, 0.6. Then voltage 110, 120, 130. Current 2.5, 3, 3.
Can you repeat, sir?
Repeat what?
Current.
2.5, 3, 3. Wattage of bulb 200, 400, 600. Time taken for 5 revolution 290, 90, 90, 45. Third reading is 45. Next, we'll go for half vein opening. Half vein opening, constant speed, half vein opening, speed 1000. Pressure gauge 0.1, 0.2, 0.3. Vacuum pressure 40, 40, 40. Head over V notch H1 0.1, 0.1, 0.2. H2 0.5, 0.5, 0.5. Then voltage 130, 120, 120. Current 2.5, 2.5, 3. Wattage of bulb 200, 400, 600. Time taken for 5 revolution, capital T 225, 85, 55. 225, 85, 55. Okay. Now that I have given you the readings, you will have to calculate the readings for the efficiency for first set of readings for constant speed and constant head. I'll leave the calculation open like this. Do the calculation. First reading efficiency for constant speed, first reading efficiency for constant head. You tell me, okay? Do it now.
So why are we taking different head values for constant and speed? H1, H2 are different for all readings.
See, calculate only input power and brake power. This torque is not required for that load. You're not using a this thing, dynamometer. That's not required. Only find efficiency using brake power, input power. That's all. Anybody getting the value? Anybody getting the values now? Yes.
Sir, for brake power,
Hmm.
how do you get the F1 and F2?
Yeah, that's what I'm telling. Don't think about F1 and F2. We are not using dynamometer. That's what I told. Don't take anything. All this not required. Just output power. Put the time taken for 5 revolution. You will get the output power kilowatts. Don't take this one. This is for mechanical loading. This is not there. Here you have electrical loading. Not required. Only substitute the value of T and find output power. That's all. Yes, what is the value? Yes, what is the value of efficiency?
So 53.
Correct. 53. And for similarly for constant speed also.
So, but break power value is more than input power value.
How? For which one?
For the first one, constant head.
No, man. What is W? What is the value of W? Tell me. What is the value of discharge? You tell me. Yes. Now, what value you got for discharge? You tell me.
1.9.
1.9 into 10 power minus 3.
Hey, no, man. 4.9 into 10 power minus 3. How did you get 1 point something? See, capital H is a small h. That is the difference of h and. See, I think you have taken h1 minus h2. It is the difference of h and. If you take the h as the difference of h1 and h2, you need to add it, not subtract. Okay, it is a
We
difference.
added only, sir.
0.25 plus
Yes, sir, we added.
0.75, so it will be 1.0. Correct.
Yeah.
H. Then, so H into this is
Yes, sir.
12.6. So 1 into 12.6 will be 12.6 only.
12.6.
Fine. Now H is 12.6 here into G, A1, A2. A1 is pi by 4 D1 square. A2 is pi by 2, pi by 4 D2 square. So D1 is 25 mm, D2 is 12.5 mm. Okay. D1 is 25, D2 is 12.5. Remember. Next, HM is equal to 10 into P. So what value of P you got? Put that value of P, find HM. HM into discharge into W. W is equal to rho into G. It will be 9810 only. W 9810 into discharge value into HM value. That will be head on the turbine. That you will get input power. Brake power. What is the time taken for a revolution? First reading? It is 130, 130. Put that value here in the place of T. See here, this is not the torque. They have made a mistake. This T is the time taken for 5 revolution. This T is the last column, time taken for 5 revolution 130. You have to put 130 there. Don't take that formula. T is F into F1 minus F2 9.81. That is for mechanical loading. Don't take that one. 5 by 1500 into 60 divided by 130 into 0.75. That is your P naught value. Okay. Now you tell me what efficiency you will be.
So what you told only we did, but Q value we both did and we got same. We got 1.9 into 10 power minus 3.
Okay, tell me what is the efficiency value? Tell me.
Brake power is coming higher than input power. Input head. I mean input power.
Brake power is coming higher.
Yeah.
Oh. Here discharge is 4.9 into 10 power minus 3, man. What they're getting.
So that is A1 value is coming as 4.9 into 10 power minus 3.
A1 value, huh?
Yes, sir.
Just check it. Check it again.
So Q value is coming same only, sir. 1.9 it's coming.
Into 10 power minus 3.
Yeah.
Okay. 1 second, wait. Check out. A1 is how much? Pi by 4. Pi by 4 into d square, no? D1 is 25 mm. Okay, pi by 4 d square. So 0.49, correct? Huh? A1 is 0.49.
No, sir. Like 4.9 into 10 power minus 4 will come. In meters, you have to do, no, sir.
I know. 3.14 divided by 4 pi by 4 into d square. D is how much? 25 mm. That is 0.025. 0.025 meters. 4.9 into 10 power minus 4 you will get. Okay.
Yes, sir.
So that is the discharge. Next.
No, A1, no, sir.
Sorry, A1. Sorry. Then A2 is 3.14 divided by 4 into, this is 12.5 mm. So 0.012. So 1.2 10 power minus 4 is A2, correct?
Yes, sir.
Okay. Next, H is how much? Capital H?
12.6.
12.6.
12.6.
12.6. So multiply that divided by root of A1 square minus A2 square. Do it again, check it and tell. How much are you getting? Discharge? Somewhere you are making mistake. That's all.
No, sir. Same it's coming.
Okay, so whatever value of discharge, you keep it. Then HM is equal to 10 into P. What is pressure gauge reading? 0.2. 0.2 kg per centimeter square. Remember. So how much you got for HM? 0.2 kg per centimeter square. Remember, you have to convert to meters now. H into, that is 10 into P. There I think you have done the conversion mistake.
To convert something there, sir.
That's what, HM 10 into P. P is in which unit? Kg per centimeter square. You have to keep it in meter square, no? How you will keep it? It is in meters of water column. Check it. ಅಲ್ಲಿಗೆ ಲ್ಯಾಬ್ ಒಳಗೆ ಹೋಗಿ. So HM is equal to 10 into, what is the pressure? Pressure gauge reading.
0.2 into 10 power minus 4.
Now tell me what is the input power, what is the output power? No? No. Tell me. No. Oh, no, I mean, the lab actually, and in the class. No, nothing. HOD has shared the whole exercise. Yeah, now tell me what value you are getting. Yes, what is the reading? Not getting? Yeah, can you tell me? Become much smaller. What is the mistake then?
So if we do centimeter square to meter square, the power difference will be 10 power minus 4. So the value difference also goes by that much.
Correct. Now you take directly kg per centimeter square and you multiply by P, that 10. Wait, where is 1 second? See, if PV is the vacuum pressure, then where are we taking this vacuum pressure into consideration? What is the use? We are not taking PV anywhere, no? PV value we are not taking anywhere. Correct.
Yeah.
Only pressure gauge reading P we have taken here. Isn't it? So, I think you will have to use this formula is there, no? To convert. to convert kg per centimeter square to meters of column. Okay, we'll check it. We'll check it. And this is the reading. And here also they have done some calculation mistake. Let's see what will happen. So anyway, you know the calculation, right? Next class, I'll just clarify with you. There could be some error in the reading. Okay, we can do that. Okay. Next class, I'll just tell you how to do the calculation. The other things are okay. Everything is fine. But are you sure that efficiency is coming? That is output power is greater than input power. I mean,
Yes, sir.
sure. Huh?
Yes, sir.
I'll just check it out. I'll speak to the lab coordinator Sripadivakar also, and I'll get back to you. Okay. I'll see what mistake there is there and why they are given vacuum pressure. They're not considering it all here. I'll check it out. Okay.
Okay, sir.
And next class I'll tell you. Apart from that, it's okay. Right. So with this, we have completed the Francis turbine also. We are left out with only one thing, that is the Kaplan turbine. Okay. And we have to do one open-end experiment, which is the Bernoulli's principle experiment. It's a small experiment. I'll give you the reading. You have to do it and write in the record. Very important. Open-ended experiment means something new, which is not in the syllabus. Additional experiment, what they call. Okay. So next class will be next Wednesday, 30th. So that day I will finish Kaplan turbine and give the readings for the Bernoulli's principle open-ended. Okay, that's a small one. So once I give that, the syllabus will be completed. So by 30th, I'll be finishing Kaplan turbine also and your syllabus also, so that you can study for your third test. Okay?
Yes, sir.
All of you comfortable with it? Yeah. Yeah, so Wednesday I'll be doing Kaplan turbine and the open-ended experiment or the additional experiment. Okay. With that, we'll be concluding the fluid mechanics lab. Okay. And I think HOD sir has asked you by mail confirmation those 28th to 2nd January, you have to come to the lab. So your consent he has asked. So all of you give your consent, whatever you want to give. And 30th will be the last experiment, Kaplan turbine. Regarding lab internals, I am not yet sure. Very shortly they will announce. So kindly complete all your lab records, whatever is pending. Do see January 16th is the last working day. I don't want everything to pile up. Now at least you finish part A and minimum of part B at least. Start uploading everything. I have been repeatedly telling you, upload your records immediately, so that I can also evaluate and give your marks then and there. Okay. So next class 30th will be the last class where I'll finish Kaplan turbine, then the open-end experiment, and we can end the fluid mechanics lab. Okay. So any doubts you have in this, that is the only calculation part. I will talk to Sripadivakar also, and I'll get back to you next class. And that's it. Okay. If that's all right. Any doubts, please?
No, sir, no doubt.
Okay. Pardon?
Yes, sir.
Okay. Then we'll conclude. Thank you.
Thank you, sir.
Thank you. Bye. Yeah. Thank you. Bye. Yeah.